Good afternoon, everyone. Thanks for coming. So I'm going to be talking about the Hadoop-based storage tiering that we call it intelligent move store or intelligent migrate store. So it'll talk about the problems that we face today in terms of hardware-based tiering, and then where the tiering is going in terms of cloud-based storage in private or public cloud, and then move away from there and then talk about what kind of solutions people are looking at from a customer standpoint as well as from a developer standpoint. So it'll talk about pretty much, moving from how to just storing it. One of the problems that happens today, and I'll give a background on that, is people just want to store their stuff and do a read or write. They don't really want to worry about, when I say people, it's the customers or general users. They just don't want to worry about all the intricacies of what is happening in the back end. Do I move it to a disk? Do I move it to a faster disk? Do I move it to an SSD and all? And those kind of stuff today, as it happens, either it is too much transparent, which really happens in today's hardware-based storage tiering platforms, or it is too much evident that you have to select the policies to make sure after this threshold is met, you move it to an SSD, you move it to a disk, you move it somewhere else, tape or whatever. So those are the problems that people are facing today. I guess it's trying to move to the next slide. Okay, I got it. So I'll start the talk with this kind of stuff that Albert Einstein mentioned, is that a lot of times, and even today, what is happening is people are trying to solve problems by fixing them in the actual products that are there, which means if you have a problem in HBase or if you have a problem in MongoDB with scaling and all, for example, you actually go in and then solve that problem, right? But it's kind of a zero-sum game. You add more features, but then you have to add those features at the expense of something else, which means if you want to improve your write latency, right, then you have to sacrifice reads. Like, for example, I'll give an example of Cassandra. It's highly optimized for writes, but then querying those writes is an issue, right? So you can't optimize for writes and then also optimize for reads. Otherwise, you have to keep your indexes in memory, and that's where another problem happens, which is how big is your memory, right? If the node goes down, you lose all those updates. So those are the problems that we looked at. So where are we today? There are problems with existing solutions. So tiered architectures are good for performance, utilization, in terms of your disk-based storage. So you have SSDs. So take for example, the storage tiering platforms, the hardware that you have from EMC or Hitachi and all. Pretty much you have SSDs in the front end, then you have disks, and there is a threshold that has to be met before the migration actually starts, right? So what happens is, pretty much by that time it's too late. So the goal here is, the entire premise is, those kind of hardware-based storage tiering platforms are really not designed for big data solutions. In big data, what happens is, there is, as some people might have noticed in Twitter talk, where they talk about storm, right? The data comes and it goes, right? So there is small data that comes in chunks. You have to analyze it, and then it goes to persistent storage. So your data that is cold today may not be cold tomorrow or after an hour. You might want to read that data. That kind of entire paradigm is a little bit different than the way the entire storage tiering platforms or even the file systems have been designed. So there is a problem there. Information that is used to move data is historical. So what happens is all these storage tiering platforms, they pretty much look at the historical data, analyze it, and then move it to the better storage platforms like SSDs or whatnot. But what happens is with big data, a lot of stuff changes on the fly. So then you really have to bring it back from disk to SSD because it's required, or you do a cache miss, you bring it back to memory, do your analysis, and then put it back to the disk, right? So all that churn happens, and with big data, that's a problem. So if the data is cold, doesn't mean in future it will be cold. It can become warm or hot. So the whole premise is you have data that is hot, then becomes warm, and then becomes cold. The hardware-based tiering platforms that we have today are pretty much designed with that concept in mind, which is you have hot data, put it in SSDs or RAMs. You have warm data, maybe put it in flash or SSDs, and then the cold data goes to the disk or tape, right? The disk is the new tape. This talks about the common approach. Pretty much, with Hadoop, and primarily, when you have cloud-based systems, you have thousands of LUNs, thousands of VMs where you have to store them, right, and you have to retrieve them. How do you really do that? That entire ecosystem is actually moving at a very fast pace, right? And to manage that, the existing solutions that exist today are really not scalable. When I say scalable, means in terms of managing them and also scaling them. There are some of the cloud vendors that have actually rejected the block-based, file-based system storage solutions because, one, they are very costly, and the second thing is managing them requires higher level of skill set. That is second. And the third one that is most important is that the cost of operating those storage systems is very high. So you really have to think at, if I want to provide my cloud storage like Amazon's S3, do I really want to use some of those systems like that? And then look at, like some of the companies, even Amazon came out with their DynamoDB, where it is based on SSDs. So how do I guarantee the throughput, but at a cost which is, acceptable to the customer? So these are some of the, there is a gradual shift that has been happening. And this is just a background I wanted people to, go across. So you have key value pairs, tabular, columnar for document stores. Various ones are actually used for various purposes, which means that if you have key value pair, you might use Redis and Tokyo Cabinet because you have in-memory kind of stuff that has more value. So if you use MongoDB, you have a lot of good writes because it does the memory mapping of the document into the memory map. You don't hit the disk, you just do a write and it goes to the memory, and then later on it's flushed back to the disk. So that's something that MongoDB does. But still the problem that happens is each one of them is optimized for a particular use. One might be optimized for writes, one might be optimized for reads. But as a user, if I want to use something where I don't have to worry about all these intricacies of reads, writes, then how do I manage a heterogeneous system? That's becoming a real problem today because in an enterprise customer base, you have Mongo, you have HBase, CouchDB, and a bunch of other NoSQL stores, and they are all scattered. So either I have a single single view of that, like a single namespace, maybe use an HDFS as a persistent store, which is read-only, and then pull pieces of it into the various NoSQL stores, and then put it back. That's one way to look at it. Otherwise, I don't have a global view. So it's a little bit farther off, which is people are today able to manage. So I'll give an example of what we did was we were able to store about 1 billion documents, about 200K each onto MongoDB. And then what happens is beyond that, you hit the limits. There are some of the sacrifices that you have to do in terms of sharding. With sharding, you have to look into some of the stuff are the policies that have to be met before the sharding starts. And there is a penalty to that. That is one piece. So similarly, what happens is you reach the limits of what NoSQL data store you pick if your volume grows. So how do you really manage that? And one other thing that happens is, and I'll talk about that here is, let me go to the next slide. I guess that slide is later. But it's pretty much the 80-20 rule, which is, only 20% of your data is used 80% of the time. That's the basic premises or the assumption under which we have pretty much looked at designing this system. So if 80% of my data is used by only 20% of the time or vice versa, then what kind of storage solution do I want, right? So for example, and I'll move on to the next slide after this, is I have 1 billion documents, and out of that, 20% of the documents are used 80% of the time, which means 200 GB of MongoDB, for example. I'm just not picking up on MongoDB, but it's just a case study that we did was you store everything in MongoDB, 1 billion documents, and assuming that is, say for example, 1 terabyte, 200 GB of those documents were actually used 80% of the time, right? If you store all those 1 terabyte into MongoDB, for example, you reach the limit, right? Then you have to run into sharding, you have to do a lot of other stuff to at least manage the throughput that you were getting when the data was less, which means if you were having document size of that data space of 200 GB, how do you maintain that when you grow to 1 terabyte? That's a real problem for us. So one solution to that is, why don't you move the 80% that you are really not using out of the MongoDB, right? And then scaling that 200 GB is very easy. I get the same performance, and my throughput is good. I can really manage it, right? And not worrying about the cold data, because I'm anyway not using that cold data, right? So that's the basic premise of what we looked at. The other thing that's happening is, people are looking at transitioning from proprietary storage platforms to a more, like in Amazon S3-based storage, which of course has its own limitations on, throughput and latency, but it's still cost-effective, and I can put a lot of stuff there cost-effectively. So how do I really do that? That is what exactly people are looking for in a majority of use cases. So are there any NoSQL trends that people want to look at, which is, can I use HDFS? Because it does auto-replication of 3 as the default and then go beyond that. And if you look at it, most of the storage tiering platforms, they pretty much, if you have RAID and all mirroring, they come at a cost. And also the important thing that we looked at was, in large enterprises, you have mix and match. You have vendor A giving you storage tiering platform that you decided today. Tomorrow another vendor comes, you buy that one because it's cost effective, it has some of the other features. But how do you mix and match? So over time, say 5 years, you have a mix and match of all these storage tiering platforms that really don't talk to each other. So if you take vendor X and your data is all on SSD, you are 80% full. If you want to increase efficiency, you are asked, okay, why don't you buy some more SSDs? And you become less than 50% full, because that's when you will get the required throughput, right? But on another hand, the tiering platform from another vendor, you have 80% of the SSDs free or not allocated. But you really can't, you either have to migrate the data here, or if you have various vendors, how do you do that seamlessly, right? There is a migration that has to be done. But as a user, I would rather not worry about that complex migration and the policies that are set in place by each vendor, and just go ahead and buy SSDs, right? So that is one problem that exists today. If you look at storing the data, you don't want to really worry about replication, RAID, and mirroring. All that stuff to a user is immaterial. He just wants to store his data and wants to get his data when he wants it, not worrying about replication, not worrying about anything else. So what if you can use HDFS or NoSQL stores? The goal here is, if I want to efficiently use in software the storage tiering, I really have to understand the read-write patterns, which means how do I trap a read that is being done by a NoSQL store 1, log that, and then if it's a read and write, then how do I mitigate that? So I need to know in the last 1 hour how many reads and writes were done, so I can really decide and present to a user or alert him, these many reads and writes are happening on MongoDB, these many reads and writes are happening on HBase, and you're really reaching your limit. So how do you really manage that is a big problem. Today, that kind of stuff is not available. You might have that from a vendor A, but that vendor A's system doesn't talk to vendor B's system, so they are pretty much stuck. You might have SSDs from 2 vendors, they don't even talk to each other. Then you are stuck with one type of storage tiering platform not very much utilized, it's underutilized, and another storage tiering platform which is overutilized. So how do you really manage that cost effectively, right? I want to be able to migrate based on certain characteristics, but not worry about it. If I have SSD somewhere else available, why don't you migrate? And I'll tell the system, migrate it there, and let me do the reads and writes based on the pattern. After an hour, if something changes, let the system figure it out. So this is just a small example of, based on the access pattern, you can move the data to the right storage engine depending on the preset policies. So if you have, 10% writes that are there going to HBase, if it is more than 50 GB, maybe it will go to HBase, otherwise less than that, go to Mongo. That's just an example what we tried, and it really helped us a lot in terms of how do you really manage those things. So it does it in a transparent way. So one of the things I wanted to mention here was the average storage utilization in the enterprise is only 37%. So coming back to the other assertion that I made earlier was all these storage tiering platforms that even if you look at, they're pretty much not utilized at all. You might have SSDs, you might have disks, flash and all, and if you aggregate them, you might have 40% of them utilized. Rest of all is underutilized. The problem is it's the fragmentation. So in a single vendor X storage tiering platform, you might have SSDs which is 80% full, but the disk itself, the disk systems there, the SATA drives, they're pretty much 1% utilized. So you pretty much have stuff sitting there because your threshold has not been met, so you haven't moved the stuff from SSDs onto the disk, the rotational disk storage subsystem. And similarly, vice versa happens on another storage subsystem. So that is one piece that happens. And then the other thing is, with the traditional RDBMSs, they are really not tuned towards massive reads and writes. And when I talk about massive reads writes, why I talk about that is because when you do analytics, you have to do a lot of that stuff, on and off, and it's data coming. You have to do your queries. Then you load the data, you transform it, take the noise out, get some analytics done, store the structured data, and then run some more visualization on that. That kind of workflow is a little bit different than what RDBMSs have been written for, and the underlying file system. So the two key takeaways here is, it's the database systems and the file systems. They are really not tuned towards gearing or helping the big data applications that are doing stuff differently. So usually what happens is file systems are designed towards many applications accessing the file system at the same time. But with big data, what happens is you have a single application, but you have millions of users accessing the same data. That kind of pattern is a little bit different. So the file systems that we use today, even of course, Hadoop HDFS sits on top of the local file system. It still has limitations there. You have the B trees to scan for reads, for updates. You still have all that stuff, and hence some of the limitations that we have so far seen, of course, in Hadoop 1.0 and 2.0. some of those limitations have been removed. So if you look at this, as I was talking about, your 20% of the data is used 80% of the time. That's the premise which we wanted to look at, which is how do I now move the rest of the 80% somewhere else, not worry about it, and efficiently utilize it, because the current NoSQL stores, obviously, because it's a zero-sum game, after a certain point in terms of volume, they reach scalability limits, and that's what affects their performance. So the whole premise is, how do you really not reach the limit of that? And the assumption is that you will not reach that limit. Because if you looked at previous slide, 37% of the enterprises say that, a lot of enterprises say that 37% of the data is not utilized, right? So how do you really use efficiently the data storage platform? So this talks about what are our customers wanting. They want better cost, less floor space, cost of ownership, and hence you will be able to manage vendor X and vendor Y platforms or storage tiering platforms in a cost-efficient manner. So you would rather use a software-based approach, which is tunable, changeable, than a hardware-based approach. So another key here is I would rather use software-based storage tiering platform than a hardware-based, which is vendor agnostic. It doesn't worry about X vendor versus Y vendor. So this is another use case where if you have all the data stored in homogeneous storage, it's pretty much a big waste. Like SSDs, everything is stored there. So if you have all the 1 billion documents that I earlier talked about, and if you only use 20% of those, 80% of those should not be stored in Mongo, for example, right? So the goal is move them to somewhere else where it is much more cost effective. You might want to move them to HBase. So that is the premises that we looked at in our use case. This talks about, your hot data goes to the costliest storage. How do you qualify, right? And in my couple of slides later, I'll talk about how do you really qualify data as hot, cold, or warm, depending on read-write patterns. But that actually changes every hour or every few minutes, depending on how the data is coming and how the data is consumed, as well as the noise that you have to take it out, right? So that kind of really puts pressure on some of these storage systems, including NoSQL, to reach the limits. So a lot of users actually want visibility into what's happening to their storage. If you use the hardware-based storage platform, tiering platforms, what happens is, based on preset policies, the daemon will kick in and start migrating your data from SSDs to rotational disk and then back. But unless until that threshold is met, you still keep on writing even your cold data to SSDs. That's another problem that we see within the hardware-based storage platforms. So if you do that in software, you can easily manage and retune that faster, or write some of the machine learning algorithms to really predict, okay, what is it that's going to happen. So that's another layer that you can put on top of the existing, some of the systems that we have, and then control your management of the data. So the current hardware storage tiering platforms are expensive, and the key here is the last bullet, which is there is no mix and match. So vendor lock-in is there. If you are going with vendor X, you are pretty much locked in there. Vendor Y, you are locked in there, but how do you interoperate, right? That is where the real problem is. I might have vendor X, vendor Y, and then a bunch of other systems, and they are all stuck together. But if I want to have a global namespace to get analytics of, I have 10 chunks of 1 terabyte each, and this entire stuff is 10 terabytes. I want to be able to have a layer that actually talks to that 10 terabyte and tell me what is happening or actionable insights into that data. But that really cannot be done because all that stuff is fragmented. So how do I put a layer on top of that? And as a user, my goal is to look at all that data and make inferences out of it. Today, it's very hard. I'm not saying it's not doable, but it's hard to do that. I have to talk to one storage platform, then another storage platform, and really make sense out of it. So that's where the BI comes, the complicated BI stuff that I have to do to make sense of that. This is another use case where, mixing of hardware storage media plus the other forms of software technologies is what allows us to do that using iMStor. So if you use software-based. So the goal here is I can mix and match SSDs and rotational disks, but at the same time, I can also decide what type of data goes to what type of NoSQL stores, because that's the real beauty of it. So multiple SSDs, multiple NoSQL stores based on the read-write patterns. And I'll talk about how we actually looked at implementing that. So if you look at the stuff here, the last bullet is mix and match. So you can mix and match hardware, and then you can mix and match storage, which means that if I have a storage subsystem which has SSDs and rotational disk from vendor X, and I'm not talking about the storage, hardware-based storage tiering setup, because they are much more monolithic and they won't allow you to mix and match there. But pretty much, I can mix and match that stuff. And through software, I can have policies that will allow me to do things that earlier I was not able to do. That is one. The second thing is I can actually build analytics on top of that, which tells me that my data last 1 hour, this part of this chunk or this whole was in SSDs and the rest was in rotational disks. And then how do I migrate them back and forth? So the same capacity is there, but it's fragmented. With software-based tiering, I can take care of the fragmentation and move around without increasing my cost. So if you look at this, these are documents or emails. So a lot of times people have this issue with emails, right? Your IMAP or POP3. Pretty much you have a limitation of certain gigabytes or MBs, and then you have to store it locally or some other storage, right? And the reason is you have to back up all that stuff and all. So how do you really manage efficiently your offline emails or documents? There are some of the storage engines, they are there. So if, for example, if I have all these N documents, I can use MongoDB when I want high throughput, consistency, and master-master or master-slave kind of replication. The application has these many operations. So pretty much at the core, we actually monitor the operations, which are reads, which are small, or larger reads. So for larger reads, you might want to use HBase, for example, which is what we've seen. Its performance is pretty good. Or for smaller reads, we might want to use Mongo for storing documents, which is what we saw during our analysis. So the list actually is goes on in terms of types of storage platforms that you can use, depending on the operations that you do, which is true even today, right? If you have 90% of the reads or 90% of the writes, so Cassandra, for example, is highly optimized for writes, and then when you query them, you run into issues. Of course, the reads are okay, but it's not that fast, right? So that part type, those many reads when you're doing, so if, for example, if you're doing reads on HBase, you might want to move those kind of reads into SSDs. So at least take the benefit of that read, because you could do random reads, and on SSD, because there is no seek time, you could actually get block 1 versus block n at the same time. There is no seek time there. So those are the kind of scenarios that we looked at. So some of the candidates for migration can be, if you have small random reads, data in disk and in HBase, and then large reads without much disk seeks are stored in Mongo on SSDs. You might want to migrate that data, like the documents, from HBase to Mongo and on SSDs. And then the reverse is migrate the MongoDB data to HBase and on disk. So if you see here, you're pretty much saving cost by migrating stuff onto a software-based storage, but from disk to from SSD to disks. So your cost goes down, but at least you get the same performance. So that's the whole premise. You have all the pieces of storage there, but they are not really efficiently managed. And coming back to the same thing, which is, it's a zero-sum game. You lose something if you do optimize for reads or writes, and then you lose somewhere else. So combining the efficiencies of various subsystems, hardware as well as software, you really can achieve much more efficiency without increasing your cost. So if you see here, data on HDisks plus HBase can be moved to Mongo and SSDs because you have smaller reads and high throughput that is required. Or the vice versa is you have large sequential reads, you would want to move them to HBase and then move them onto disk. And then that's way you really take care of that piece, which is not spend too much on SSDs. The other observations that we saw was in Mongo, for example, the moment you turn off fsync, because fsync actually allows you to sync to the disk, but it's there is a penalty to that. Everything slows down. So you might want to migrate those to HBase. Some of the other stuff, if you look at it, migrate the MongoDB or CouchDB because HBase is tightly coupled to HDFS, and there is an append worm which is read only, write many. I mean, write many, read many times. Write once, read many times. That's the property which is tightly tied to anything that's built on top of HDFS. So you have that problem that is inherent there. No matter how much optimization you do, you're pretty much still stuck with something that you have built upon, which has this append ability not to be able to append to something, right? You can't do random writes. So how do we do that? The core migration engine, what it does is it monitors reads and writes. And what we do is there is a library that actually we actually contemplated on putting it in the user level. Like for example, I'll take an example, take a step back and take an example of Oracle. The way Oracle works is if it wants to optimize stuff, it actually has its own part of libc that is backward compatible, POSIX library. But it does some other stuff that the traditional libc won't do. So that's the premise that we took, which is take the same libc, change it, right? But that is done in the user space. If you want to be more efficient, you would want that to be done in the kernel space, which is what I think Facebook, I was talking to a gentleman here yesterday. Facebook has something called flash cache that they download it as a loadable driver into the kernel and then manage that stuff there. So we could actually do some of this stuff in the kernel, because ultimately all that Hadoop and NoSQL stores, they are all sitting at the user level. So you're, no matter how intelligent you can do your reads and writes, still the IO scheduling is done by the operating system. So how do you really, because that's where the magic happens. You can do all that stuff, but in the end, if the system is blocked by some of the other stuff that's happening, your stuff still will get queued at the disk level, because some of the other processes are also writing to the same local disk. So you're stuck there because the OS. And since this whole NoSQL or Hadoop sits at the user space level, you still have to interact with the OS and at the mercy of OS to do the scheduling of the IO and some of the other stuff, prioritization. So we looked at some of the reference counts, the IO stalls, the random reads and writes, and how do you really qualify a data as, like I was talking earlier, hot, warm, or cold, and then send user the alerts. The other problem is, if you run your daemon in the backend, there is a cost to that. So how do you really avoid that? Some of the problems there also we looked at. If you look at this, there is a core migration engine that we have, and I have a diagram in the end of this presentation that a little bit, I'll spend some more time on that so people can get some idea into what I'm talking about in terms of the various pieces of how we want to manage the software and the hardware storage as such. So there is a two-tiered document storage engine where the metadata actually can be stored in SSDs, and the actual documents, you can store it in rotational disks to reduce the latency. And what I'm talking about here is you might contemplate or argue that these are some of the things I can do it, but if you look at a broad user base, you have to know each and every NoSQL store, which means you have to know Mongo, you have to know Couch, the benefits of one versus the other, where one is stronger than the other, and it takes a lot of time, right? And then that's pretty much not efficient at the user level. So the last bullet talks about, you want to monitor the user space requests, And then some of the operations, as I was talking about, you might want to migrate them into the kernel space, because then you don't have to worry about the context switching that happens. So from the user space, there is a context switching that happens because you use pretty much the system call. And if you load it into the kernel, then you don't have that penalty. So you can do a lot of that stuff much more efficiently, because ultimately that is what really gives you the benefit of improving your reads, improving your writes, throughput, and latency. This is another side, like I talked about. If you move it to the system side, the other problem that really happens is, if you look at Cassandra, right, one of the problems that we saw is beyond about 50 GB or 60 GB, the garbage collector kicks in, right? If I have data which is, say, 200 GB, the garbage collector kicks in and it starts collecting all the memory that's pretty much not used and move it to the free list. And the only thing that the system at that time is doing is running GC. It's not doing anything else. So that's a real performance hog. It's pretty much running, and then some. What happens is, if there is a heartbeat that is missed, that node pretty much is brought down. If your GC is running, it's running as part of the kernel, right? And then if a heartbeat message comes, because you are getting the heartbeat message at the user level, you really may not be able to context switch into the kernel and respond to that heartbeat message. And then what happens is, the system that's sending the heartbeat message thinks that node is down and brings the node down. So that's one of the things that happens because your system is overutilized. You're running the garbage collector and memory is not enough. The assumption here is memory is still scarce. If you have n megabytes of GB of memory, then you don't have worry. But in a traditional practical system, you still have limitation on the memory that you have. So the other problem is you might want to replace random reads and writes carefully. And most of the stuff which is based out of HDFS, the random reads and writes still are very much, they are limited by their capacity, because HDFS still is, it's not appendable, it's not still very efficient. So this assertion here is we have not still used the Hadoop 1.0, and we are waiting for 2.0 to come out to see the performance. What I've been told is HDFS performance will be improved by about 35 to 40% when the 2.0 or 1.0 we start using it. We haven't yet used it because we wanted to get some of the stuff which is stable. Let's move on to the next one. So this is another use case where if an application is a game, right? It's a gaming system, and you are sitting on top of Mongo and Couch. You might want to use all the data per player onto maybe, one is single node and migrate it to Cassandra, because it is very good in writes. And when the player plays stuff, it has to cache the positions. Those positions are actually stored in NoSQL store. So you might want to use that instead of some of the other HBase and all, use it to Cassandra because it's good for writes, right? Of course, querying them is hard, but it's still better. The other thing is, as you might be aware of, MongoDB uses memory mapping, mmap, to map the parts of the file into memory, and it's just a read and write. You don't have to use IOCTL calls to write, go do the context switching, hit the disk, and then come back. So that is something that happens. So you might want to look at that, and that is some of the stuff that our migration engine in the kernel actually looks at. So this actually is, I have a copy of this diagram that I can distribute, but I'll actually be happy to email the slide deck if people are interested. So I think I'll stop here and open up for questions. Any questions? Or any thoughts people have in terms of what we have been looking at or the observations that we've had?
SSD has the PQ and hash rate per vendor.
Right.
Do you consider that as well?
Yeah, so one of the things we looked at was there are types of SSDs, and one of the things we saw was if you do too many reads, which is random reads or random writes, right, then over time the voltage on the cell was actually not there, and there were data problems. So that is another thing that we actually looked at, but we haven't tried here. The reason is there are so many vendors with so many SSDs that one is it's not very cost effective for us to try all those. The second thing is what we feel is it is still premature that you know, SSDs today are fine, but I think they might want to use the ECC kind of memory, the error correction stuff there, but it's the enterprise set of it. So to answer your question directly, no, the good enterprise level SSDs are costly, and we are trying to not base our solution depending on the type of SSDs that people use. So that's pretty much, but of course we looked at the throughput and the latency. So at that level, yes, we looked at throughput and latency. Does that answer your question? Okay, sure. Any other question?